Welcome to Nardar Academy. In this video, we are going to discuss about infinite series. Okay, so this video covers what is meant by an infinite series and how to check whether the given infinite series is convergent. So different methods which are available for checking the convergence of a given infinite series are discussed in this video. Okay, let's start with the definition. An infinite series. See, let un be a sequence of real numbers. Already I have uploaded video for sequence and how to check its convergence. I have done so many problems. Okay, you check that video for better understanding. See, suppose un is a sequence of real numbers, then the expression, that is u1 plus u2 plus etc plus un plus etc, sum of the infinite number of terms, which is denoted by sigma n equal to 1 to infinity un, is called infinite series. See, all these un are what? They are elements of this sequence, and we are finding the sum of all these terms. Okay, so this is called infinite series. Here the summation runs from n equal to 1 to infinity. Okay, suppose if all the terms of the series are positive, right, that is un is greater than 0 for all n, then it is called a series of positive terms. Okay, suppose we have a infinite series in which all u's are positive and they come alternate in sign, that is plus minus alternately if it is coming, no, this series is called alternating series. Okay, all u's are positive only, but look at the symbol here everything is positive, but here plus minus alternately coming, no, that is called what? Alternating series. Next one, we are going to define partial sum. See, infinite series means by the word itself you can say infinite series means it is sum of infinite number of terms. So for checking its convergence, we need to take its partial sum. Partial sum is nothing but, okay, Sn equal to u1 plus u2 plus etc up to un. That is Sn means sum up to the first n terms. Okay, then what is S1? First partial sum, that is A1 alone, U1 alone, S2 equal to U1 plus U2, S3 means what? U1 plus U2 plus U3. Okay, in that way we get a new sequence, and that sequence is called sequence of partial sums, right? So why do we bother about this sequence of partial sums? See, whenever we talk about something which goes up to infinity in mathematics, we have to discuss about its convergence. Okay, then only we can talk about its validity, right? So for checking the convergence of a given infinite series, this is one method of checking. That is, instead of checking whether the series is convergent or not, we have to check this sequence of partial sums whether it converges or not. So if the sequence of partial sum converges, then the series is also converges. If the sequence of partial sum diverges, then the series is also divergent. If the sequence of partial sum oscillates, then the series is also oscillating. Okay, so this is one way for checking the convergence of a given series, right? And another one important property is that, see, this is an infinite series, no, it goes up to infinity. So just by adding or removing a finite number of terms from the given series will not have any effect on its convergence, divergence or oscillation. That is, you have an infinite series, you remove 10 or 100 terms from it, it won't affect the convergence or it won't affect the divergence. Okay, so by removing a finite number of terms will not have any effect on its convergence. And similarly, multiplying the term by means of a fixed non-zero real number also don't have any effect on the convergence of the series. Okay, right? Then I have a necessary and sufficient condition for convergence of a infinite series. Only a necessary condition, not a sufficient. A necessary condition for a series sigma un to converge is that un tends to 0 as n tends to infinity. That is, un means what? Nth term. If the nth term tends to 0, okay, that is the series converges. Okay, what is the necessary condition? Un tends to 0. See, this has to be handled carefully. If the series is convergent, definitely nth term tends to 0. But if the nth term tends to 0, that doesn't mean it is a convergent series. Okay, I will give you example later, right? So convergent series implies un tends to 0, but un tends to 0 need not imply your convergence. Okay, right. Next one is a series of positive terms converges if and only if there exists a number k such that u1 plus u2 plus u3 plus etc. un less than k for all n. That is, for showing that a series of positive term convergent, it is enough to show that the sequence of its partial sum is bounded. This is nothing but partial sum only, no? So for proving a series of positive term is convergent, it is enough to prove sequence of partial sums is bounded. Okay, next I have some comparison test for checking the convergence. Okay, see, let un and vn be two infinite series of positive terms. Suppose first comparative test is un is less than some k into vn. Each term of the series u is less than k times terms of vn. Then what is this k? Fixed positive number. Suppose if Vn is convergent, then Un is also convergent. Suppose if Un is divergent, then Vn is also divergent. So what do you mean by this? See, all the elements of Un are dominated by Vn. Less than means how do you say? Un is dominated by Vn or Vn dominates Un. So whenever the larger, bigger series itself is convergent, the smaller series will also converge. Okay, right? And whenever the smaller series is divergent, that implies the bigger series or larger series is also divergent. Okay, right. Next one, suppose I have un lies between some kvn to capital kvn. In that case, both converge or diverge together. The same reason as before, this un is dominated by kvn and this un dominates this kvn. Okay, as like the previous case, whenever this is convergent, this will be, sorry, whenever this is convergent, this will be convergent, and whenever this is divergent, this will be divergent. Okay, so both converge or diverge together. The another test is, suppose you take un by vn and limit of this is equal to a finite non-zero number, then also un and vn converge or diverge together. Okay, and the next one, un by un plus 1 is greater than vn by vn plus 1. In that case, vn converges implies un converges. Un diverges means vn diverges. Right? Okay. Next one. This is a harmonic series 1 by 1 power p, 1 by 2 power p plus etc. 1 by n power p. This is convergent for p greater than 1 and divergent for p less than or equal to 1. Next one is Cauchy's nth root test. This is used for testing convergence of a series of positive terms. See, nth root means what? Un power 1 by n. You take limit un power 1 by n and take it as L. If this L is less than 1, then the series converges. Diverges for L greater than 1, and for L equal to 1, the test fails. Suppose if this limit is infinite, then the series diverges. Next one is D'Alembert's ratio test. In this one, we find the ratio of un by un plus 1 and we take the limit as n tends to infinity. Okay, and if the limit is greater than 1, then the series converges, and the limit is less than 1 means series diverges. For L equal to 1, the test fails. As like nth root test, if the limit is infinity, then what do we say here? Here we said it is divergent. Here we say it is a convergent series. Next one is Rabb's test. Sigma un be a series of positive terms, okay, such that limit n tends to infinity, n into un by un plus 1 minus 1 equal to L. Then the series converges for L greater than 1, diverges for L less than 1, and test fails when L equal to 1. Almost in all the tests, when you get the limit as 1, the test will be a failure one. If the limit is equal to infinity, then the series is a convergent series. Okay, then the next one, Cauchy's condensation test. So this test says, suppose I have a sequence of positive terms f of 1, f of 2, f of 3, etc. such that f of 1 is greater than f of 2, that is, this is a decreasing sequence, greater than f of 3, etc. for all n. Then sigma f of n and sigma 2 power n into f of 2 power n converge or diverge together. Next one is Commerce test. Let sigma un be a series of positive terms, and let this is a divergent series. 1 by dn be a divergent series of positive terms such that limit n tends to infinity dn un by un plus 1 minus dn plus 1 is equal to L. This series converges for positive value of L and diverges for negative value of L. Okay, next one is Gauss test. Let sigma un be a series of positive terms such that un by un plus 1 can be written as alpha plus 1 by n into beta plus 1 by n power p into gamma n. This alpha is positive, p is greater than 1 and gamma n is a bounded sequence. Then what about the convergence of this series? For alpha greater than 1, alpha is greater than 1, no need to check beta and gamma. Directly you can write the series is convergent. If alpha is less than 1, the series is divergent. For alpha equal to 1, you check beta. If beta is greater than 1, the series is convergent. If beta is less than or equal to 1, it is divergent. Okay. This Gauss test can be applied. When the RAPS test fails, you can apply this one. Okay, then few more tests we have. One is Bertrand and De Morgan's test. So this test says if limit of log n into n un by un plus 1 minus 1 is equal to L, then this series converge for L greater than 1 and diverge for L less than 1. Next one is Maclaurin's integral test. For x greater than or equal to 1, f is a non-negative monotonically increasing integrable function such that f of n equal to un. Okay, then sigma un and integral 1 to infinity f of x converge or diverge together. Next one is logarithmic test. This test conveys that if limit n into log of un by un plus 1 is equal to L, then for L greater than 1 the series converges, for L less than 1 the series diverges. Next one, Leibniz test. This is for alternating series. Okay, the alternating series u1 minus u2 plus u3 minus u4 etc. is there, no? With un plus 1 is less than or equal to un and un tends to 0 implies the series is a convergent series. Okay, so these are the tests available for checking the convergence of an infinite series. I will post the problems using all these tests in the next video. Okay, thank you.